Welcome to Future Talk. On today's program, we're going to talk about some of the latest frontiers in space exploration. I have two guests from NASA's Ames Research Center. William Borucki is the chief scientist and driving force behind the Kepler mission, whose purpose is to search for Earth-like planets in other solar systems. And Anthony Colaprete is the top scientist and leading inspiration of the Elk Cross Project, which recently discovered water on the Moon. We'll talk about these and other projects, including the Mars Rover. We'll get some insights into the culture of space exploration and also discuss the practical benefits to people here on Earth. We're going to start with a video of the Kepler mission, courtesy of NASA, and then we'll come back and discuss it. So let's go ahead and roll that tape.
We have an innate curiosity about our origins. Is life in our galaxy common? Does it exist? Are we alone? How unique is life here on Earth? The Kepler mission is one step in answering that question.
The Kepler mission is a huge step forward in answering the question, what is our place in the universe?
The Kepler mission is NASA's first mission capable of finding Earth-like planets orbiting other stars in the galaxy in a region around the star we call the Habitable Zone.
The Habitable Zone is where we think water will be. If you can find liquid water on the surface, we think we may very well find life there. So that zone is not too close to the star because it's too hot and the water boils, not too far away where the water is condensed and ice-covered, planet covered with glaciers. It's the Goldilocks zone. Not too hot, not too cold, just right for life.
The primary science goal of Kepler is to answer the question if Earth-like planets in our galaxy are common or rare. Kepler is going to detect planets via the transit method. What we aim to do is to measure the brightnesses of stars very, very accurately for a very long period of time without blinking, so that when the planet passes in front of the star, the light output from the star is going to dim just a little bit. That star is going to blink for about 12 hours, and we will be able to measure that dip in brightness. And it's that dip that we call a transit.
Kepler is a different animal from the Hubble Space Telescope or the Spitzer Infrared Telescope because it doesn't take pictures. You won't see beautiful images that you see from Hubble because we're not doing that kind of science. Those types of missions like Hubble and Spitzer are designed to focus on specific targets.
If you hold your hand at arm's length with a grain of salt or a grain of sand, that's about how much of the sky you can see with a normal astronomical telescope at any one time.
Kepler has a field of view that's 10 degrees by 10 degrees.
Our field of view is about as big as your hand at arm's length, covering the sky.
So rather than taking pictures of very concentrated parts of the sky, we're looking at taking a very broad snapshot of a lot of stars.
Kepler takes really fuzzy pictures, but the thing that Kepler is designed to do, and it does very well, is look for very small variations in the brightness of the stars.
An Earth-like planet passing in front of a Sun-like star is going to cause the brightness of that star to dim by only 1 part per 10,000. That's like looking at a headlight from a great distance and trying to sense the brightness change when a flea crawls across the surface. But the Kepler instrument is designed to detect such small changes in brightness.
The Kepler sensors are CCDs. The CCD in your camera is about the size of one of your small fingernails. The CCD chips on Kepler are a couple of inches square in pairs, and there's 42 of those. In your camera, you might have a few megapixels. If you have a really nice camera, you might have 10 megapixels.
We have 96 million pixels, and they have very low noise, so we can find very small planets.
Once Kepler is launched from the Earth, it will go into what's called an Earth-trailing orbit. Astronomers call that a heliocentric orbit, which means sun-centered orbit.
It looks at the stars continuously, day and night, 365 days a year, and it slowly moves away from the Earth, orbiting the Sun by itself.
And from there, it will point itself at the Kepler field and stare at the Kepler field nearly without blinking for 3.5 years at least, maybe longer if we have an extended mission.
That was our video of the Kepler mission, and now I'm talking with Bill Borucki, who is the driving force behind that mission. Now, I think that video was put together before the Kepler mission was actually put into space, but it actually is in orbit right now, is it not?
That's right. It's been in orbit for about a year now, so we have about a year of data.
And have you found what you're looking for?
We've certainly found planets, and we've found several hundred candidates. Many of them are quite small, toward the size of the Earth, but they're candidates. You've got to look at them very carefully, make many different kinds of measurements to make sure that you're not being fooled, because lots of things look like a planet. If you have a big star and a small star across the big star, you think it might be a planet. So there's a lot of ground-based work that's done after we come up with these candidates, these several hundred candidates, as we show which ones are really a planet and which ones are not.
Now, once you determine that it's a planet, what else can you tell about it? For example, can you determine surface temperature, whether it has air or water or other useful things?
We can tell quite a bit about the planet. First of all, we get its size. For the bigger planets, we actually get its mass. We get its density. We can tell you whether the planet is sort of a fluffy planet. We found some planets that are less dense than Jupiter, some planets, in fact, that have a density of styrofoam. Giant planets with very low densities. We're working our way from the big planets to the small ones, because it gets more and more difficult as you go from big planets to small ones. And similarly, if you're trying to find planets in a habitable zone, then you've got to see them when they have long period orbits. The Earth takes a whole year to go around the Sun. We have to wait about 3 years, so we need 3 transits before we say, yes, we found something, let's verify it from the ground and announce it. So up to now we have announced about 5 planets. They're short period planets, and they're giant planets. This coming year we're making our observations to qualify these candidates. We expect to find planets quite a bit smaller than Jupiter, maybe some that are super-Earths.
Now, let's say you discover planets that are Earth-like. Is there any follow-up? I mean, they're still so far away we could never get there unless we have radically improved means of propulsion.
Well, that's right. Certainly, it's, we're in a stage where we're still learning to develop new space propulsion systems, and people like Tony may talk about that, in fact. So we're developing new space systems, but most of these stars are very, very far away. What we're trying to understand is not about the nearest stars, but about stars in general. Are there lots of Earths? If we find hundreds, and we expect to find hundreds, that means there are lots of places for life. There's probably life throughout the galaxy. If, on the other hand, we don't find any, we have the capability of finding many, then we might be alone. That'll be the end of Star Trek, of course.
All right, so we'd have no purpose, but, well, maybe we'd have the whole place to ourselves.
Yes.
But this is a really complicated project with very little margin of error. What would you say is the most difficult thing about putting together the Kepler?
There's so many good possibilities for missions. We need to know so much about space. Kepler has to be so much better than other missions that people believe it will work well, and it will give them a breakthrough in our knowledge of our galaxy. That's what's required.
Is there a follow-up? Is there another Kepler beyond this Kepler? You're mapping one segment of the sky. Mm-hmm. Is the goal to just keep doing more and getting more and more pieces?
Kepler is a step, and that was mentioned earlier. First we found planets, ground-based planets. Now we're in space, we're finding planets as small as the Earth. We'll learn out whether they're frequent or not. Now, if they are frequent, then the next step, the next mission, will look at that, blank out the star, look at the spectra of the planet, and tell you about its atmosphere. If they're very rare, then the mission that will follow us is a much bigger mission. The first mission is very expensive. The second mission, which requires many telescopes to look very far out to find enough transits, enough planets, is extremely expensive. So the National Academy of Sciences has told us, find out how many they are and which kinds of stars they're around, and then we will build a mission to follow yours to find out about their atmospheres.
Okay. We're going to go on to the Elk Cross mission, and Tony, you've been the principal driving force behind that. Now we have a short video of that mission. This is an animation and there's no soundtrack, so I'm going to ask you to provide a running commentary and then we're going to come back and discuss it further.
Okay.
So can we go ahead and roll that tape?
So the Elk Cross Mission took advantage of a spent upper stage of the Centaur rocket that propelled us to the moon. And in this part of the graphic, the green line is the trajectory of the Elk Cross Mission. You see it flew by the moon and then went into a large elliptical orbit around the Earth. And finally it catches up to the moon after about 4 months and impacts the moon. Here you see the two components of the Elk Cross spacecraft, the spent upper stage, which is the large white cylinder, and then the shepherding spacecraft, which was the paneled, smaller spacecraft at the back. What we're doing here, this shows the final portion of our mission. 9 hours before we impact the moon, we separate from that spent Centaur. The shepherding spacecraft spins around to get its sensors. You'll see it do a braking burn. We wanted to observe the impact close, but not that close. So we do a little braking burn to put a little distance between us and the impacting Centaur, and we trail it all the way into the moon. We did the separation. We were about 9 hours out from the moon. The separation we achieved was 4 minutes, so we were trailing 4 minutes behind. We targeted a permanent shadowed region at the south pole of the moon. After impact, the shepherding spacecraft flies at the impact site, gathering data real time, flying eventually through the debris cloud itself and impacting itself on the moon about 4 minutes afterwards. And that's what this artist rendition shows here. And you can see the conceptual ejecta plume coming up out of the dark crater as we head on in and impact ourselves. And this is as it may have looked from the surface if you were observing it, if you were so lucky to be standing on the moon while it happened.
Okay, so that was our video of the Elk Cross Project, and I take it that that video was produced before the mission itself, but the mission itself has taken place already, I believe, in 2009.
Yeah, it impacted last October.
And what did it find? It was looking for water. Did it find it?
Yes, we did find water, and more importantly, we found a particular flavor of water we were very interested in, and that's water ice. Leading up to the Elk Cross impact, there were some other observations by other missions orbiting the moon and some that just flew by the moon that sensed water bound in the minerals of the moon.
Which would make it hard to extract?
Very hard to extract and at very small concentrations. It'd take a football field area of lunar dirt to make about a small cup of water. Here, what we found was gallons, hundreds of gallons of water concentrated in one area. So the concentrations were much greater, and they're water ice, which really indicates an origin for the water. It helps us understand actually the processes that have been affecting the moon.
When you say you detected a certain amount of water, you mean that's how much was kicked up by the impact, not how much remains?
No, so we made a very small little impact onto a much larger crater. The crater we impacted, Cabeus, is about 100 kilometers across, and the shadowed region that has temperatures that are exceedingly cold, minus 240 degrees below 0 centigrade, was many hundreds of kilometers across an area. Our crater we made was about 30 meters across, about the size of a tennis court. And the ejecta that flew out of that, the debris that flew out of it was, we saw approximately more than 4% water content in the debris that flew out of that. That translates to several hundred kilograms worth of water.
Now we have some still pictures of the Elk Cross mission also. We're going to show those pictures and discuss them. So can we see the first slide, please? Okay, so there it is.
So this is the instrument suite for the Elk Cross payload. So what was very unique about the Elk Cross mission was the unique vantage point we had from the shepherding spacecraft. As we flew directly down at the moon, we used these 9 instruments that were all integrated and built at NASA Ames with commercial industries from across the United States to make the measurements that I've just described. They include 5 cameras, spectrometers, and radiometers that basically separate the light and look for the various components that could make up the materials.
And that was able to send all the information back to Earth before it itself crashed?
It was all what we call bent pipe, real time. We had about a megabit per second relay to Earth And so it took data, immediately transmitted it to Earth because you had no storm forward on this mission.
Okay, now we have another picture here. It looks like
this shows the two spacecraft that went to the moon together. So the top gray spacecraft is the Lunar Reconnaissance Orbiter, which sat on top of the LCROSS mission. The bronze cylinder below it is the LCROSS shepherding spacecraft. The two project managers, Dan Andrews, the LCROSS project manager, and Craig Tooley, the LRO project manager, are the fellows there in the garb. And we were what was called a secondary payload. LRO was the primary mission. It's in orbit around Moon, making incredible measurements now. We were just a secondary part of that. What you see here in this image is the Atlas rocket that lifted both vehicles to the Moon. And the upper segment is called the Centaur. It is what we actually took advantage of. Otherwise, that's ditched in the ocean. We held on to it, and that's what we turned into our impactor.
Okay. And I gather this was a fairly fast and inexpensive mission because you used rockets that were already available. You didn't have to invent everything from scratch.
It had to be that way. It was an opportunistic mission. LRO moved up to a larger launch vehicle and had some extra capacity to the Moon. So NASA put out a call saying, what could you do with this? 19 proposals went in, and LCROSS was selected. The rub of it was you had to do it in 2.5 years and for a very small amount of money in relative terms. And so LCROSS had to rely on existing hardware, existing technologies to put it together. One engineer put it very precisely that nothing could be developed just glued. We just basically glued together as quick as we could a spacecraft, a payload, and got it off.
Sounds efficient. Sounds like that's probably the best way to do it. You know, we have another video, our third and final video. This is about the Mars Rover. Actually, there are two rovers, identical twins, I believe, on opposite sides of the planet. We're going to see a video about that and then come back, discuss that, and also some other topics with space. So let's go ahead and roll that tape.
For a 90-day mission, I remember when we landed, we were excited. We would have 3 months to explore this region around our landing site, and we've basically blown the doors off that. For 6 years now, we've been doing classic field geology on Mars, learning about the planet and its ancient past, and there have been powerful revelations that have come well after that prime mission.
This experience of Spirit is something that I've really kind of integrated into my whole identity. This has become part of what I do, and it looked at the very beginning of the mission like this was going to be something that I got to do for a very brief time, for 3 months, and that was terrific, and it was unique, and it was special, and I was really looking forward to it, and I never in my wildest imagination believed it was going to go on for years.
Spirit really has had to have a lot of spirit to keep going. It's been the little rover that could, in a way. It's had to work very hard for all of its discoveries.
2 years into the mission, so well past the prime mission, the right front wheel stopped working, and the wheel doesn't spin. So when we drive backwards, dragging that wheel, and it would cut a furrow. And so it actually turned out to be yet another scientific instrument or scientific investigation, because it now trenched as we would drive along, revealing what's just beneath the surface.
One thing that we seem to be finding almost anywhere we're digging this trench are these widespread deposits of various kinds of salts and minerals. They look this brilliant white or yellow in the color images, and that's because they're either sulfur or silica or salts of various kinds. And the really important thing about these minerals, and salts in particular, is that the only way they form is with water. So the fact that we're finding these salts is real evidence that there was hot water over a very widespread area, not just little isolated pockets. Mars really could have been a place that supported life. And without these rovers driving over these vast distances, far beyond their expectations, we would never have known that.
That's one of the great discoveries that Spirit did well after its prime mission, and as a result of one of the most serious mechanical failures we've had on either rover.
Mars is a pretty harsh place. We've had dust storms before. We have really low power situations in winter. We've had other small glitches that have caused us some tense moments. But the Spirit seems to always find a way of turning some kind of adversity into something positive.
We have a very ambitious stationary science campaign for the rover. I mean, for 6 years, we've been driving both Spirit and Opportunity, not really taking any time to stop and smell the roses. There's a lot of lander science that one can do, and we plan to do that with Spirit.
Spirit's continued triumphs absolutely amaze me. Just the fact that we've had so much more of this mission than we ever thought we were going to have.
What these rovers have done is that they have made Mars a familiar place. Mars is now our neighborhood. My team goes to work on Mars every day. And that, I think, is the great intangible contribution from these rovers, is that Mars is no longer this, strange, unknown world. I mean, yes, it's still mysterious, but much of Mars is now known to us as a familiar place.
And that was our video about the Mars rovers. I really find this fascinating how familiar Mars has become. He said that, we go to work on Mars every day. Well, we've really made some huge strides there. I have some questions, which, either one of you could feel free to answer. It said in the video that there's evidence that there was once a lot of water on Mars. So the question is, where could it have gone and why don't we see it now?
Well, certainly some of the water has gone into the ground and been frozen, and people have found that water. Some of it, of course, goes into the atmosphere. When it goes into the atmosphere, there isn't any ozone to protect it. So the ultraviolet light from the sun breaks it up into hydroxyl molecules and hydrogen molecules. Hydrogen is gone forever, just leaves the planet. The hydroxyl with the oxygen goes to the surface, oxidizes the rock, and the rock becomes red. And your oxygen is forever locked up in those rocks, not as water, but as oxygen.
So does that mean that the water cannot be recovered at this point if people were to go there?
Well, certainly the water that's frozen in the ice and the surface could be recovered. Might, in fact, have some remains or some signs of ancient life. So that should be recoverable, but once the hydrogen leaves from a water molecule, you don't reconstitute it.
At this point, we have explored pretty much all the planets of the solar system and pretty much all their moons. What would you say are some of the most interesting and unexpected things that we've discovered in our own solar system in the past 10 years?
By far, the fact that we're getting water spraying out of the moon Enceladus around Saturn has been dramatic. It indicates there's an underground, there's an ocean there, under the ice. Maybe it's 1,000 feet of ice, but there's water there. And when there's water, there's a possibility of life. Even in the Antarctic, where things are very, very cold, people find some life under that ice. And so that's very, very exciting.
And for me, I would say, to the other extreme, the coldest temperatures observed on the moon now by the Diviner mission, our instrument on LRO, are as cold as 28 degrees Kelvin. So those are temperatures colder than Pluto. So some of the coldest temperatures in the entire solar system are right in our backyard at the moon. And those are acting as fantastic cold traps, gathering material for billions of years.
Is that just because it never faces the sun?
That's right. It's always in shadow. Some of these areas are always in shadow, and without a tangible atmosphere around the moon, the heat can be easily dissipated and not blown back in by atmosphere.
Have we shed any light on the origin of the solar system? One theory is that the sun and all the planets and moons condensed out of the same ball of gas. Looking at the chemical composition of all these bodies, does that theory hold up, or is there maybe some other explanation?
One of the most dramatic things that we have found in the years that we've been finding these extrasolar planets is how very, very different those planetary systems are from our own. We really felt that we understood our planetary system. The small rocky planets were close to the sun when it was formed because ice couldn't condense, it was too warm. The ice would condense to form the Jupiters out a long ways from the Earth. What we found is just the opposite. We found Jupiters with 3-day orbits or 4-day orbits way inside the orbit of Earth or Mercury. The orbits in our solar system are rather circular. They're elliptical, but a little bit. These orbits are very elliptical. So it's been astounding. Our planetary system looks so different than every other planetary system we've ever seen that we're more puzzled about our own solar system today than we were 20 years ago.
That's true. You know, one thing I'm interested in is the whole culture of NASA. How do the space scientists do what they do? Is there some method of organization? Do ideas come from the top down or percolate from the bottom up? How do people work together to produce these extremely complicated projects with almost no margin for error that can't possibly be serviced after they've left the Earth?
Headquarters has a good system. Basically what they do is they want to do good science. They want to explore the galaxy, the planets, and so on. And so they advertise opportunities. And so Tony or I will see, here's an opportunity for a launch. Let's come up with a good proposal that does really great science, that makes a breakthrough. And we write a proposal, we build a team, we sketch out how this mission would go, and then we have to sell it to headquarters. And they have competition. It's typical to have 20 or 30 missions for one opportunity. And so they look at all these missions and say, which one is going to succeed? Which one is going to make that breakthrough? And only those get selected. Very competitive. But you can see it's the interplay between what headquarters brings to us, this opportunity, and what the individual scientists bring to headquarters in terms of doing the great science.
And a lot of NASA is guided by community opinion, and that's, again, emphasizing the point Bill's made, is that NASA headquarters, and through these calls and through what we call studies, decadal studies every 10 years, listens to the community, asks the community, what are the priorities we need to study? What is the top scientific questions we need to answer? And they use that community input as guidance. So in a large part, it is a bottoms-up percolation from the individual scientist, like Bill or myself, who say, I've got this idea and this is why it's important. And then NASA follows those ideas.
Well, this is extremely interesting because we only have about a minute left, so this is going to have to be quick. But you know, space research is extremely fascinating, but it's also extremely expensive. What is the payoff for the taxpayer? What benefits does the person on the ground receive from all this exploration?
He receives a great deal of benefit. First of all, space exploration requires very high technology. So we help our industries become technologically competitive with the rest of the world. We build the products, we invent the products, we build the jobs here in the United States. And we also, I think, provide the spirit of exploration that people in the world in the U.S. would like. They understand better their place in the solar system, their place in our galaxy.
Great. I'm going to have to cut you off because we are out of time. I'd like to thank my two distinguished guests, Bill Borucki, Anthony Colaprete. Thank you both for being here today. Thank you for watching. I'm Marty Wasserman. We'll see you next time.